Today, we're tackling a problem that challenges us to find the largest possible square that can be formed from a given set of rectangles. The twist: we need to count how many of these rectangles can actually contribute to forming that maximal square. It's a great exercise in careful iteration and tracking. You're given an array where each element is a rectangle represented by its length and width. For each rectangle, you can form a square whose side length is limited by the smaller of its two dimensions. Our goal is to first identify the maximum possible side length among all squares that can be formed. Then, we need to return the total count of rectangles that can form a square with that specific maximum side length. A straightforward but slightly less efficient approach involves two passes. First, iterate through all rectangles to find the maximum possible square side length. This means, for each rectangle, calculate the minimum of its length and width, and keep track of the largest minimum seen so far. Once you have this global maximum side, you then make a second pass through the rectangles. In this second pass, for each rectangle, if its minimum dimension equals our previously found global maximum, increment a counter. This works, but it requires iterating over the entire input array twice. The time complexity is big O of n because of two passes, and space complexity is big O of 1 constant time. The key insight to optimize this is to combine the two passes into one, using a dictionary to store counts. As we iterate through each rectangle, we calculate the potential square side length for it, which is the minimum of its length and width. We then use this side length as a key in our dictionary. If the key already exists, we increment its value. Otherwise, we add the key with a value of 1. Simultaneously, we maintain a variable to track the maximum side length encountered so far across all rectangles. After processing all rectangles in a single pass, our dictionary will hold the frequency of every possible square side length. The maximum side length variable will already contain the global maximum. Finally, we simply retrieve the count associated with this maximum side length from our dictionary. This avoids the redundant second pass. Let's trace this with our example, rectangles 5, 8, 3, 9, 5, 12, and 16, 5. We initialize our maximum side to 0 and an empty dictionary. First, rectangle 5, 8, minimum is 5. We update our dictionary to store 5 with a count of 1 and our maximum side becomes 5. Next, 3, 9, minimum is 3. Dictionary now has 3 with count 1. Max side remains 5. For 5, 12, minimum is 5. Dictionary updates 5's count to 2. Max side is still 5. Finally, 16, 5. Minimum is 5. Dictionary updates 5's count to 3. Max side remains 5. After processing all rectangles, our maximum side is 5, and we look up 5 in our dictionary, which gives us a count of 3. The final answer for our example is 3. This is correct because the largest possible square side is 5, and there are 3 rectangles, 5, 8, 5, 12, and 16, 5, that can form a square of side 5. You'll spot this pattern when you need to find a maximum value, and then count occurrences related to that maximum. It's also a strong signal when you realize a two-pass approach could be optimized by storing intermediate results, like frequencies, in a hash map or dictionary during the first pass. Time complexity is big O of n due to a single pass through the rectangles. Space complexity is OS, where S is the number of unique side lengths encountered for storing the dictionary. This dictionary-based approach is super efficient for frequency counting problems. Try the next problem, same pattern, just a different twist. Don't forget to like and subscribe for more DSA insights.